Dear students, in this short video, let us learn a little bit about the orthogonality and orthonormality of wave functions. How do we express these two conditions? These are expressed as integral psi m star psi n d tau is equal to 0 from minus infinity to plus infinity. How can we state this mathematical condition in words? It means that different eigenfunctions corresponding to different eigenvalues are orthogonal. Consequently, if the integral is expressed in this manner, psi n star psi n d tau, this is equal to 1. Obviously, this gives the total probability, and which is always equal to 1. 1 reflects 100% over here. So if we want to state these two conditions together, by the way, I should write that this is orthonormal. This is the normality condition, by the way. Normality condition. Now if I want to put these conditions together and write them together, I may write integral minus infinity to plus infinity psi m star psi n d tau is equal to 0 for m not equal to n is equal to 1 for m equal to n. Now let's choose a wave function, say for a particle in a box. It is written as psi is equal to under root 2 by L sine of pi x by L. So as an example, we are choosing a particle which resides inside a box of length L. So here it goes. This is a one-dimensional box whose length is from 0 to L, and we have a particle inside it. The wave function for this type of a case is chosen to be written like this. Psi is under root of 2 by L sine of pi x by L, where L is the length of the one-dimensional box. Now, let us find the probability of finding the particle inside this box. So we'll write it as integral, of course the limits will go from 0 to L, right? Under root 2 by L sine of pi x by L. Again we'll write under root 2 by L sine of pi x by L dx. Now if you look at this condition, for instance, or this condition, right, this wave function does not carry any complex factor like iota, so its complex conjugate will be similar to itself. So for psi n star, I have written the same wave function under root 2 by L sine of pi x by L, and for psi n again I have to write under root 2 by L sine of pi x by L dx. Now this and this factor, they combine and come out, so we get 2 by L outside. Integral 0 to L. Now I have sine square of pi x by L dx. Now I hope that, of course, I'll write probability on left hand side. What we are calculating is basically the probability of finding the particle inside this one-dimensional box of length L. Now I hope all of you are aware of this basic trigonometric expression that twice sine square theta is equal to 1 minus cos of 2 theta. So we can conveniently use this expression over here. So what are we going to write? 2 by L, and for this I'm writing integral 0 to L 1 minus cos of 2 pi x by L dx, and then we can take this factor of 2 in the denominator, which will be here. If you are okay with that, let us proceed. So this expression, beyond this we can write it as probability is equal to 1 by L. Inside you have integral 0 to L 1 dx, that is dx, right, minus integral cos of 2 pi x by L dx. Again the integration goes from 0 to L. Now I hope you recognize that this expression is 1 by L. For this it is x only going from 0 to L, and I hope you remember that this integral is 0. So this is 1 by L. Here it is L minus 0, that is 1 by L. L, that is equal to 1. That implies 100%. Now why is it so? Since we have chosen the entire range of this length from 0 to L, and we know that the particle has to exist. Definitely it has to exist somewhere in this range. Therefore the total probability of finding this particle is 100% in this region. Instead, if I had chosen a limit say 0 to L by 2, then you would say that this result would have changed to 50%. Our outcome should have been 1 by 2, that is 50%. So this is how we calculate the probabilities if we are given the wave functions of a given case.